afternoon and welcome to all of you to our day 2, session 3 of International Conference on Advanced Materials in Innovative Technology MT 2022. And a very warm welcome to our chairperson Dr. Mahavir Prasad Yadav for chairing today's session. Dr. Mahavir Prasad Yadav is an assistant professor in Department of MIT School of Applied Science, MIT University, Jaipur, Rajasthan. He has earned his PhD from MNIT Jaipur and post-graduation from Central University of Rajasthan. He has participated in several international and national conferences and workshops and published more than 10 research papers in reputed journals.
So I welcome Chairperson Dr. Mahavir Prasad sir. Welcome sir.
Thank you very much, ma'am. Thank you very much. Am I audible?
Hello.
Am I audible?
Yes. Sir.
Okay.
Welcome,
Thank you.
sir.
Thank you, ma'am.
Can we start the session?
Yes.
Okay, so we start with our first paper. That is paper number 124, Gajendra Yadav.
Okay. Yes, Gajendra Yadav.
Yes.
Yes, sir.
Yes, it's visible.
Good afternoon, everyone. I am Gajendra Yadav, PhD scholar, and under the guidance of Dr. Mahavir Prasad, Department of Mathematics, MIT University, Rajasthan. My topic is application of fractional calculus in groundwater flow problems. The outlines are introduction and integral transformations, fractional operators, applications, and references. Introduction of fractional calculus. Fractional calculus is a special branch of applied mathematics that deals with derivatives and integrals of arbitrary orders, including complex orders and their application in science, engineering, mathematics, economics, and other fields. It is also known as generalized integral and differential calculus and calculus of arbitrary order. And this is the history of fractional calculus. Isaac Newton and Leibniz independently discovered calculus in the 70th century. In recognition of this remarkable discovery, Newman quoting that the calculus was the first achievement of modern mathematics, and it is difficult to overestimate its importance. I think it defines more equivocally than anything else the inception of modern mathematics and the system of mathematical analysis, which is its logical developments, still constitute the greatest technical advance in exact thinking. Leibniz first introduced the idea of symbolic method and used the symbol dny by dxn. This is the nth derivative of y. And L Hospital asked Leibniz about the possibility that n be a fraction. What about if n is equal to half? Then Leibniz replied, it will lead a paradox. But he added, prophetically, from the apparent paradox, one day useful consequences will be drawn. And Lacroix developed the formula for the nth derivative for y is equal to x to the power m, where m is a positive integer. Then the nth derivative of y is m factorial upon m minus n factorial into x to the power m minus n. And in the equation 1, the fractional derivative of x to the power beta, where alpha is any fractional number. The most important advantage of using fractional order differential equation in mathematical modeling is their non-local property and memory effect. It is well-known fact that the integer order differential operator is a local operator, whereas the fractional order differential operator is non-local in the sense that the next stage of the system depends not only upon its current state but also upon all its preceding states. And the memory means an existence of output at the present time that depends on the history of the change of the input on a finite or infinite time interval. Now we discuss integral transform. The integral transform of a function fx defined on a closed interval ab is defined in equation 2, where capital K x comma k is kernel of the transformation, where x and k are two variables, and the Laplace transformation is defined in equation 3. This is the simplest form of the integral transformation, and in the equation 4 inverse Laplace transformation is defined in equation 4. In equation 5 Fourier transformation, and in equation 6 inverse Fourier transformation are defined. And the fractional operators in the area of fractional calculus and its applications in many branches of science and engineering, several fractional derivatives were mainly utilized. The most common used were Capito and Riemann level fractional derivative, which were successfully utilized in modeling complex dynamics, appearing in physics, biology, engineering, and many other fields. Riemann level fractional integral is defined in equation 8, and the Riemann level fractional derivative has some disadvantage, like derivative of the constant is not equal to 0. Then we used capital fractional derivative most of the time. Then the capital derivative allows initial and boundary conditions to be included in the formulation of the problem when solving the real world problems. The capital fractional derivative is more suited than the usual Riemann-Level fractional derivative in several engineering problems because of its better relation with the Laplace transformation. And the capital fractional derivative is defined in equation 13. And in equation 14, the Laplace transformation of capital fractional derivative is defined. Definition of capital fractional derivative involving non-singular kernel given by Capito and Fabrizio by changing the kernel x minus t to the power minus in equation 15 with the function e to the power minus alpha x minus t upon 1 minus alpha, where this is the exponential function. So in equation 15, capital Fabrizio fractional derivative is defined, and in equation 16, the Laplace transformation of capital Fabrizio is defined. The aim of capital Fabrizio fractional derivative was to introduce a new derivative with exponential kernel. Its antiderivative was the average of a given function. The derivative introduced in equation 15 cannot produce the original function when alpha is equal to 1. Then Atangna and Bologna defines new fractional derivative, which is known as Atangna-Bologna fractional derivative, which is defined in equation 17, where E alpha is the Mittag-Leffler function with one parameter. And in equation 19, Laplace transformation of Atangna-Bologna fractional derivative. Some applications of fractional calculus are the subject of fractional calculus has applications in diverse and widespread field of engineering and science such as electromagnetics, viscoelasticity, fluid mechanics, electrochemistry, biological population models, optics, and signal processing. It has been used to model physics and engineering process that are
Gajendra,
found. Yes, sir.
don't write what you have written. Okay, tell directly that these are the applications.
Okay, sir.
Okay, you are reading all these.
Um, uh, the fractional calculus used in groundwater flow problems, also used in the theory of viscous elasticity, in structural damping models, in edge detection, in fluid mechanics, and these are the references. Thank you.
Okay, so I have one question. That in equation number 4, integral transform, you are writing S. What is S there?
Question?
4. Or in 3, e raised to power minus st. So what is S here?
In this equation 3, S is S is the transform variable where we replace S, where we replace
So,
T by the S.
okay, so you write in definition L Laplace of ft, comma S. Okay, right here.
Okay, sir.
And second, there are many operators, fractional operators. So what are the need of these operators? What are the need of these? Can we use only one operator? Why we use so many operators?
So there are many operators like Riemann-Level fractional derivative and Capito Fabrizio Atangnabaleno. But in the Capito operator, we have some disadvantage because in the in Capito in equation 13, if x is equal to t, sorry sir, if alpha is equal to 1,
Okay. Then
in equation 15,
if alpha equal to
if
1,
alpha is equal to 1,
then it's
then
convert in ordinary differential equation. This is Capito Fabrizio. Okay.
yes sir,
Equation number 15. What is the problem in equation Capito operator?
in Capito,
Hmm.
this gives a singularity when alpha is less than n minus 1.
Okay, okay. Okay, so can we go to next, ma'am? Kanak, ma'am?
Yes, sure. Okay, nice presentation. So Gajen, you can remove your slides.
Okay.
Yes. So now our next presenter is paper number 77, P77, Neetu Shekhawat. Neetu, you can share your slides.
Yeah, ma'am, I'm sharing.
Yes,
I'm
it's
audible,
visible.
ma'am.
Yes, it's visible. You can start.
Good afternoon, everyone. And my topic is second and third Hankel determinants for Basilevic functions plus. And so this research article is aimed at the target of obtaining bounds for the second and third Hankel determinants for our new subclass of Basilevic functions of type beta. And we have also obtained Piketty-Szego inequality of this subclass. Here we are, the class of Basilide functions of type beta contains functions if it fulfills the condition this that real part of zeta z dash, matlab, where psi of zeta is given by equation 1.1 that is here, and we have used q derivative operator here, and which is defined as by the, and we have used the definition of kth Hankel determinant is given by equation 1.7, and Hankel determinant is a square matrix. Each of the ascending skew diagonal from left to right is constant, and we have used the certain lemmas like lemma 1, lemma 2, lemma 2, and lemma 3. We have obtained this result. If particular function is in our class, and then modulus of d2 is less than bounds. We have obtained bounds for these coefficients. We have shown this by equating the corresponding coefficients on both sides of equation 2.5. We obtain d2 is this, and d3, d4, d5 respectively, like this. And taking absolute values of these and using lemma 1, we obtain modulus of d2 is less than 2 upon beta plus q, and similarly we have obtained modulus of d3, d4, and d5 by using lemma 1 and 2. This is theorem 2.2, and we have obtained this d2, d3 minus d4. And we have done like this. This is this theorem is on Piquet's CZ2 problem. We have obtained this result. We have obtained the upper bound for this by using similar procedures as using theorem 2. We have obtained this result, and this certain remarks and corollaries we have obtained. And finally, this is second Hankel determinant H22 D24 minus D3 the whole square the bounds. We have obtained this, and using similar formulas we have obtained these results. And this is third Hankel determinant. We have obtained this, and these are references. Thank you. Any questions?
Okay, so one suggestion is you can write, you are writing something in the white page and other like proof in other part of the PPT. So it's looking like some weird. So you can use all the things in same like here. You are using theorem in white and proof in like this. Okay, so you can, okay, second thing is you are using Basilevich function. What is Basilevich function? Yes.
Basilevich function, if so you mentioned
In start, you are writing Basilevich function. Start in the PPT. Hello, am I audible?
Yes, yes, sir.
Okay. So Nitu, what is Basilevich function? No response. Okay, ma'am. Connect.
Yes,
Can go
this was
next.
our second presentation. Now we can move to our third presentation, P140, Nidhi based. So Nidhi, you can share your slides.
Okay, ma'am. Good evening, everyone.
Yes, good evening.
Good evening, everyone. I am Nidhi Bisht, and I am a research scholar under the supervision of Dr. Asaram Garola from Department of Mathematics, Doon University, Dehradun. And I am working on the approximation properties of certain linear positive operators and their variants. So moving on, today I'll be presenting before you my paper, which I have written on approximation by a new Kantorovich type operator. So first of all, we'll be discussing the abstract. We have divided the abstract into three portions. And in the paper, we have proposed a Kantorovich generalization of a summation type operator, which is basically what we have done is we have modified the Kantorovich operator to get better approximation properties. And secondly, what we have done is we have obtained the convergence and the approximation properties of our proposed operators in both uniform as well as in a weighted norm. Then thirdly, we have obtained the degree of approximation in terms of modulus of continuity. Moving on, here we have defined the operator, our Kantorovich type operator that we have defined in our paper. UNFX is the operator which is equal to n plus Sn minus 1 upon Sn, summation running from k equal to 0 to n, and again the summation running from j 1 to Sn minus 1, and then integral running from k plus j minus 1 upon n plus Sn minus 1 to k plus j upon n plus Sn minus 1, ft dt. Ft is the function, and pnkx. So here Pnkx is the kernel of our operator, which we have defined as the binomial nk, x to the power k, 1 minus x to the power n minus k x. So here x will belong to the interval, closed interval of 0, 1, and Sn is the sequence of n, which is greater than equal to 0. And we have put two conditions where for limit n tending to infinity, 1 upon Sn will tend to 0, and again for limit n tending to infinity, Sn upon n will tend to 0. Then we have calculated the moments of our Kantorovich type operator. So we have calculated them at 1, t and t square. And then we have calculated the central moments of the operator at t minus x and t minus x whole square. So basically why we are calculating this is we are using this calculation for proving the theorems that we have proved in our paper. Then moving on, we have solved the rate of approximation for our operator. So the theorem that for a function such that its double derivative exists at a certain point x belongs to the closed interval 0, 1, this equality will hold. So we have calculated the limit n tending to infinity n plus Sn minus 1 into a un fx minus fx is equals to limit n tending to infinity Sn minus 1 into 1 minus 2x upon 2 f dash x plus x into 1 minus x upon 2 f double dash x. So what we have done is we've extended the result of Warren's-Kazaa on our operator and evaluated the asymptotic error term for the operator for all the functions that are twice differentiable. So basically we have tried to improve the rate of approximation for our operator. Then moving on, we have calculated the error estimation. So for UNFX, this is our operator and a function which belongs to a continuous interval of 0, 1. We have calculated the modulus of the difference between the operator and the function, and this inequality will hold. It will be less than equal to 2 upon Sn minus 1 omega f comma delta nx. So basically we have done it in terms of modulus of continuity, and we have calculated the value of delta nx. Then we have talked in our paper about the local and the global approximation. So for a weight function phi x, which we have taken as under root x into 1 minus x, and lambda greater than equal to 0, and x lying between 0 and 1, we have calculated the inequality which we have given over here. We've calculated the value of g dash u du, integral running from x to t, and we've taken its modulus. So this is less than equal to the expression that you can see over here. And secondly, we have used this value, the first value, in the second result. So again, for a weight function phi x, we have, and for a function belongs to closed interval 0, 1, lambda greater than equal to 0, and x lying between 0, 1. We have again calculated the value of the modulus operator at the difference between the operator and the function. So we have obtained this result. Then moving on, we have done the approximation in weighted spaces. So basically, we can define the weight function. We've taken the weight function as a WPX, which is equals to 1 plus x to the power p to the power minus p. So basically 1 upon 1 plus x to the power p for p greater than equal to 0. So you can see from here clearly that for p equals to 0, the value of W0x will be 1. So now using CP, where P belongs to N0, 0, 1, 2, the set of all the real valued functions, which is uniformly continuous on 0, 1, and WPF, which is uniformly continuous and bounded on 0, 1, the norm of the norm in the space C over P, it is defined by this formula. The norm of F over P will be equal to the supremum, where X belongs to 0, 1, omega PX into modulus of Fx. Then we have proved these two results for our paper. So basically, a function belonging to C2 star 0, 1, there will hold the inequality where we've calculated the value for W2x un modulus of un f dash x minus fx, and it is less than equal to this expression that you can see over here. And secondly, we have secondly for p belonging to n0, there will exist C0p such that the norm of the operator at 1 upon WPT over P will be less than equal to C0p. And for every function Cp, f belonging to the continuous space over P, we have the norm of the operator over P will be less than equal to C0p into norm of f over P. So here is the graphical representation that we have shown in our paper. So basically, we have taken a function fx, which is equals to x cube in this case. So the blue line, it is representing the curve of x cube. Now what we have done is we have taken this function x cube and we have put it in our operator, unfx that we had talked about earlier. And we have put in x cube and we have calculated the value of the operator for n is equals to 2, 3, 4, and 5. So the lines orange, pink, red, and purple, they're representing the function, the operator at different values 2, 3, 4, and 5. So moving on, we have, this is the tabular representation of the functions of, we've calculated the values of the operator at n is equals to 2, 3, 4, and 5. So this was the last slide. That will be all from my side. Thank you very much.
Okay. So you are using Kentrovich. Where we use this?
So shall I share it again? I'm so sorry. I think I
No issue.
stopped
No issue.
sharing.
No issue. Just
Okay,
tell me where we use Kentrovich operator.
So Kantrovich operator, so basically to calculate to use some approximation properties of certain operators, and for taking out some graphical representations, we can use this operator
Where
to study
use
different properties.
on some differential equation or anywhere else?
Yes, so for studying numerical approximation also we can use.
Okay, numerical.
Calculating the rate of approximation, convergence, the rate of convergence.
And you are writing one thing, C2 star 01. What is this?
Yes, sir.
C2
So it is a
belongs
continuous. What,
yes.
sir?
A belongs to C2 star interval 0 to 1.
Yes, sir. So it is a continuous function, is continuous space over M, basically
So
where we
C2
take in M is
represents
equals to 2.
continuous. Okay.
Yes, sir.
Okay. Okay, ma'am. Correct, ma'am.
Thank you so much, sir.
Yes, so very
Next.
good presentation. Yes, sir. Can we move to our next presentation?
Yes, ma'am.
So that is P138, paper number 138, Amrita Singh. So you can share your screen.
Good evening, everyone. Myself, Amrita Singh, research scholar under the supervision of Dr. Asharam Garola, Doon University, Dehradun, India. And the topic of my paper is beta type Beskov operator with quadratic order of approximation. This is the outlines of my paper. like abstract, introduction, and so on. So start with the abstract. So when we start approximating a function with the approximation methods of a function, then approximation by a linear positive operator is the best method and a very simple method, and it becomes always order of approximation 1 by n. But we introduce a new operator, we modified operator, which is better order of approximation than a classical one. And we use these keywords like linear positive operators and rate of approximation. So introduction. Classical Vasco-Cave operator. What is Vasco-Cave operator? For a function f belongs to 0 comma infinite and x belongs to 0 comma infinite, for a function which is continuous on the interval 0 comma infinite and x belongs to 0 comma infinite, for n belongs to n, then we have a Vasco-Cave operator. Vn fx is equals to summation k is equals to 0 to infinite Pn k x f k by n. Here Pn k, which is defined as Pn k x is equals to binomial n plus k minus 1 x to the power k x to the power k upon 1 plus x to the whole power n plus k, which called kernel of our Vasco-Cave operator. And this classical Vasco-Cave operator always shows the property or order of approximation of 1 by n, which is shown by this theorem: limit n tends to infinite n, difference of operator minus fx is equals to x1 plus xf dash double dash of x. Next, Dermier operator. So the above operator, which we called classical Vasco-Cave operator, always integrate the summation type operators. But when we talk about integrable function, then we तब हम बात करते हैं इस बारे में कि हम जब हमें इंटीग्रेबल फंक्शन की जरूरत होती है तब हम डर्मियर टाइप ऑपरेटर इंटीग्रेबल फंक्शन के लिए हमें Vasco-Cave का डर्मियर ऑपरेटर लेकर आए, जिसे हमने डिफाइन किया mn k through mn x is fx, same as for f belongs to 0 comma infinite and x belongs to 0 comma infinite, and mn fx is equals to n minus 1 summation k is equals to 0 to infinite pnk integration 0 to infinite pnk ft dt. Here pnk is the same as classical Vasco-Cave operator and same property. It is called the kernel of the Dermier operator. Next, this is our construction of our operator, which is our modified operator, and this gives the better approximation property than classical one. So for that, we have first take a function which is belongs to 0 comma infinite and x belongs to 0 comma infinite, and then our operator which is defined which we defined as Sn fx is equals to n plus 1 summation k is equals to 0 to infinite q n k x integration 0 to infinite bnk t f t dt. Here bnk t f is equals to t to the power k minus 1 1 plus t to the power minus n minus k minus 1 n plus 1 b k n plus beta k n plus 1, and the kernel q n k x is equals to a xn 2v minus u minus w b xn w minus u plus u. Here axn and bxn are unknown sequences which we found by more calculations, sequence of x and and u v w are the decomposed part of our basic kernel of our operator. Next, moments and convergence properties. For moments, and before calculating the moments of convergence properties, we required some basic calculation. For that, for r is equals to 0 to 1, we have some calculation. Summation k is equals to 0 to infinite Pn. For r equals to, when we put r is equals to 0, 1, and 2, we find some basic calculation. Then next, the moments of our operator, which we find on obtain on ej. For ej is equals to t to the power j is equals to 0 1 2, j is equals to 0 1 2. So when we put j is equals to 0, Sn 1, x is equals become 1, at t it become x, and at t square it become x square plus 2x upon n minus 1. Next, the central moments of our operator. The central moments of our operator is defined as follows: Sn t minus x is equals to to the whole power 0 is equals to 1, and to whole power minus 1 is equals to 0, and so on. Next, the next next the R operator SNFX verify these condition, limit n tends to infinite and n minus 1, the central moments is equals to 0 at the t minus x is equals to 0, limit n tends to infinite and n minus 1 Sn t minus 2x to the whole power whole square, x is equals to 2x, and so on. Next, the convergence property. These theorems shows our convergence property for Sn for a function which is continuous on the interval 0, infinite, and x belongs to 0, infinite. Then norm of a function is always less than equal to norm of function. And for proof of this, from lemma 1, we see that moment of at 1 of our operator is become 1, and then limit n tends to infinite, norm of fx is less than equal to Sn1 norm of f is less than equal to norm of n. And similarly, the next theorem is the Kurokin theorem, very famous Kurokin theorem, which is very useful in our approximation theory for a linear positive operator. So if f is a continuous function on the interval 0, infinite, and x belongs to the 0, x belongs to 0, infinite, then limit n tends to infinite, Sn fx is equals to fx uniformly on the interval this. Next are error estimations. If to find the error estimation, we have to find the difference of our operator and function. Difference are operator and function. So if f is a function which is continuous on the interval this 0, infinite, and x belongs to 0, infinite, is less than equal to √2 plus 1 omega. Here omega is the modulus of continuity, and f under root of 2x upon n minus 1 and n minus 1. And next our next error estimation, if alpha belongs to 0, 1, and alpha belongs to if alpha belongs to 0, 1, and m is greater than equal to 0, then operator error estimation, it means the difference of our operator and function is less than equal to 2 omega bar alpha fx 2x upon n minus 1 to the whole power alpha by 2. Our next error estimation is based on Lipschitz class and Lipschitz relation. So if alpha belongs to 0, 1, and is the bounded subset of the interval 0, infinite, of the interval 0, infinite, then and it holds, and there is a Lipschitz class mod of active minus fx is less than equal to m t minus x to the whole power alpha, and here t belongs to ohm, which is a bounded subset of 0, infinite, and x belongs to 0, infinite. Then and m is greater than equal to 0. Then our error estimation mod of Sn minus fx is always less than equal to this quantity. And here d is what is d? Here d is the distance function between x and omega. Next error estimation is the corollary of above theorem, which is simpler. वहाँ पे हमने ओमेगा एक क्लोज सबसेट लिया था 0 से इनफाइनाइट का, बट यहाँ पे हम लोग सिंपलर वहाँ पे हम लोकली बात कर रहे थे, बट यहाँ पे हम ग्लोबली अपने ऑपरेटर के एस्टिमेशन के बारे में बात करेंगे. सो सेम एज इफ f belongs to 0, infinite and x belongs to 0, infinite, then difference of वही क्या कहते हैं error estimation of our operator is less than equal to m 2x upon n minus 1 and n minus 1 to the whole power alpha by 2 for alpha belongs to 0, 1, and m is always a positive quantity. M is greater than equal to 0. And our next property is based on weighted norm for f belongs to C star, and then our operator satisfy the limit. Then our operator satisfy these operator mod of Sn minus fx is less than equal to 6 mf. Here d is the Here D is the here D is the it is weighted norm of weighted norm. Here यहाँ पे जो D है वो weighted norm के ऊपर वो है क्या कहते हैं quantity होती है. Then these are some our estimations and these are some references of our which I used in my paper, and this for myself. Thank you so much.
Okay, so Amrita, one suggestion. You should use equation numbers. Okay, you have given many equations. So
Yes,
give
sir.
equation numbers to so you can directly see that from this equation,
Yes, sir.
and you directly tell that these are the terms. Okay. And one
Yes,
thing
sir.
you are talking about convergence error analysis. So is there any method you used in to find the convergence or error analysis? Any
Yes,
theorem,
sir.
any method?
ये सर ये जो हम ये सब जितनी भी कन्वर्जेंस ये हम जो एरर एस्टिमेशन कर रहे हैं ना, तो इसके थ्रू जो हमारी क्वांटिटी आती है, इसी के थ्रू हमारे जो अगर हम ऑर्डर ऑफ अप्रोक्सीमेशन जितना हाई जाता है उतना हमारा रेट ऑफ कन्वर्जेंस बढ़ जाता है. ये जो हम एरर एस्टिमेशन एंड ऑर्डर ऑफ अप्रोक्सीमेशन निकाल रहे हैं, देन
You are
हाँ जी,
using norm of a function.
यस सर, नॉर्म और
So-
मॉड.
Okay, so is there any theorem or anything?
yes
So
sir,
that-
yes sir, Warren's का theorem which defined order of approximation.
Okay. Okay, thank you. So now connect me. Next,
Yes.
we
Yes.
can.
So for last candidate for today's session, P54 Meenu Khan.
Yes,
Meenu,
ma'am.
you can share your slide.
Yes, ma'am. Am I audible, ma'am?
Yes, yes, you are.
Okay. A very good evening, everyone. I am Meenu Khan, and I'm a research scholar under Dr. Deepshikha Rathore from ASAS, Amity University, Rajasthan, Jaipur. And I'm going to present about the development and investigation of physicochemical properties of cobalt ferrite, silicon carbide, epoxy nanocomposites. The flow of presentation will be like this. First, we will discuss about the introduction of nanocomposite and the material we have used, and then we will move towards the objective of our work, which will be followed by the method of synthesis, and then results of discussion and conclusion. So, as we all know that the reinforcement of two or more material of different properties have been used recently, which leads to the enhancement in the several physical and chemical properties of material, which can be used in various applications, such as EMI shielding, MRI scans, memory tapes, sensors and actuators, and so on. So the fabrication of nanoelectronics devices for the benefit of society is one of the most significant tasks of the material technology due to the high chemical. So that's why nanocomposites can be used to enhance these properties and can be used in these applications due to their high chemical and physical stability. Nanocomposites are the prominent material for these demanding applications. Nanocomposites are formed with the incorporation of nanofillers in the polymer matrix. For this purpose, we have used cobalt ferrite, silicon carbide, epoxy nanocomposite, where cobalt ferrite is a nanofiller having inverse spinal structure. As you can see in the figure 1, this is the inverse spinal structure of the cobalt ferrite nanoparticles, and hence it due to the unique structures, it possesses the excellent magnetic and dielectric properties. Then we used a hetero interface is introduced by adding silicon carbide with cobalt ferrite nanoparticles into epoxy matrix to enhance the properties. We have used silicon carbide because silicon carbide is an excellent semiconductor, due to which it has been progressed much towards wafer growth technology, sensing devices, and electronic devices. And epoxy is an environmental friendly, inexpensive polymer which has a good capability to incorporate nanoparticles. So we can hope that the combination of cobalt ferrite, silicon carbide, and epoxy may bring all the separate properties together in their nanocomposite form with enhanced and efficient features. Then we moving towards our next slide. That is the objective of our work. So for our first objective is to synthesize cobalt ferrite silicon carbide epoxy nanocomposite by using chemical co-precipitation method and solid state method, and then to characterize its structural, morphological, elemental, and dielectric properties of the prepared nanocomposite. So to fulfill our first objective, we have optimized two methods, that is chemical co-precipitation and solid state method. Basically, there are several methods to synthesize nanoparticles, but we have used chemical co-precipitation method because this method is inexpensive and easily processable. This is the flow chart of the synthesis of cobalt ferrite nanoparticles, in which we have used ferrous chloride as the precursor and cobaltous chloride as the reducing agent, which were added and stirred for 15 minutes to form a complex mixture. Then the complex mixture were added to the aqueous solution of NaOH with constant stirring. After the reaction, you can see here in this picture. This is the reaction, the complex mixture of ferrous chloride and cobaltous chloride in this burette, and after the reaction we get the solution in the dark brown color. And then we do the magnetic decantation, which were followed by the centrifugation. After centrifugation, we got the sample in the form of precipitate, which were dried at 60 degrees centigrade, and followed by the grinding and calcination at 300 degrees centigrade to get the cobalt ferrite nanoparticles. So we get the cobalt ferrite nanoparticles in the form of powder of dark brown color. Then after getting the cobalt ferrite nanoparticles, we mix the commercially available silicon carbide in the prepared cobalt ferrite nanoparticles using solid state method. In this method, we have added some added ethanol and continuous mixture, and we continuous grinding leads to continuous grinding until the evaporation of the ethanol. Then after the evaporation of ethanol, we got the silicon carbide cobalt ferrite in the nanocomposite in the powder form. Then we added this prepared sample, we mix with epoxy resin and pour the mixture into the mold, which were cured for 24 hours, and we get the prepared and then we get the cobalt ferrite silicon carbide epoxy nanocomposites in the pellet form. So this process have been carried out to prepare 4 pellets with different weight percent of silicon carbide, that is 20, 40, 60, and 80%, as you can see in this figure. Then we will move towards the second objective. Our second objective, that is to characterize its structural, elemental, morphological, and dielectric properties of the prepared sample. So first, the structural properties and phase identification were analyzed using X-ray diffractometer, that is XRD, and crystalline size and phase formation of different samples were studied at the room temperature. This is the XRD pattern of the cobalt ferrite nanoparticle and the cobalt ferrite silicon carbide nanocomposite with different weight percent. The XRD pattern shows that all the samples have a single phase of cubic spinel structure, which were confirmed by the JCPDS file, and the 311 plane of the cobalt ferrite nanoparticle, cobalt ferrite, and 111 plane of the silicon carbide, which confirms the proper attachment of silicon carbide with cobalt ferrite nanoparticles and the formation of nanocomposite in a proper phase. Then the crystalline size were calculated using Schrerer formula, that is T is equals to 0.89 lambda upon beta cos theta, which were estimated for cobalt ferrite nanoparticles around 3 nanometer, and for other weight percent of the cobalt ferrite silicon carbide nanocomposite were respectively like 5 nanometer, 6 nanometer, 11 nanometer, and 18 nanometer. So we can conclude from this that as we increase the doping of silicon carbide with the cobalt ferrite, the particle size also increases. Then we move towards the morphological study of our material. The microstructure and surface morphology of cobalt ferrite silicon carbide epoxy nanocomposites was studied using SEM technique. This is the figure from figure A to E shows the SEM micrographs of sample. This figure shows the SEM micrograph of cobalt ferrite in the form of powder, and B to E shows the cobalt ferrite silicon carbide nanocomposites in the form of different weight percent in the form of pellet. And the analysis of SEM images shows that the microstructure of nanoparticles have an almost homogeneous distribution, and some of them are in the agglomerated form, which confirms the pore-free material with uniform distribution. Then we move towards the elemental study. Elemental study of the cobalt ferrite nanoparticles were determined using EDX analysis. The measurement can be used to discuss the chemical quality of cobalt ferrite nanoparticles. Sorry. This is the EDX spectrum of cobalt ferrite nanoparticles, in which the peaks are identified as the iron, cobalt, and oxygen at their respective position, indicating the presence of iron, cobalt, and oxygen in proper ratio, that is 1:2:4. Then moving towards our next property, that is dielectric property. Dielectric measurement, including frequency dependence of capacitance, dielectric constant, and laws were recorded using LCR meter in frequency range of 20 Hz to 1 MHz at room temperature for cobalt ferrite, silicon carbide, epoxy nanocomposite. So this is the figure. Figure A shows the dielectric constant, the variation of dielectric constant with the variation of frequency, and figure B shows the dielectric loss with the variation of frequency. So as we can see in the figure, the dielectric constant and dielectric loss, we got the highest dielectric constant and loss at the initial frequency, but as we increase the frequency, the dielectric constant and loss as well as loss started to decrease, and after a certain frequency it started to getting constant. It might be happen due to the saturation of polarization among the atoms. So these are all the properties we have characterized for the material, and then we'll move. Following are the conclusions. Following are the points we have concluded from this work, that we have successfully synthesized cobalt ferrite, silicon carbide, epoxy nanocomposite using chemical co-precipitation method and solid state method, and then the XRD peaks confirms the proper attachment of silicon carbide with cobalt ferrite nanoparticles and formation of cubic spinal phase of cobalt ferrite and cobalt ferrite silicon carbide nanocomposite. Then SEM images shows the proper agglomeration of nanocomposite, and EDX analysis confirms the presence of cobalt, iron, and oxygen in proper ratio, that is 1:2:4, and the dielectric constant and loss decreases with increasing frequency and found to be the highest at initial frequency. These are the references. These are some references I have used in my paper, and I would like to acknowledge UGC DAE CSR Indore for funding and all the characterizations. Thank you. That is all from my side.
Okay, Minu. So
Yes, sir.
I'm asking, is nano is some form of atom or anything? Nano.
Sir,
What is nano?
nano is the range of atom. It is the size of an atom. That is, we can say that, or we can say that nano is the size of atom, that is 10⁻⁻⁹ meter. So it's a range for the material, for the particle.
Okay. And how we synthesize nanoparticles?
So as I have already discussed, that we can synthesize nanoparticles with so many methods. That there are basically two methods, that are bottom up and top down approaches. So in top down approaches, what we do is we took the bigger particle, and using some other some methods, that is like ball milling and all, we can ball milling, grinding, we can convert them into the nano size. And then, as I have used bottom up approaches, in this we use some chemical reactions to form the nanoparticles. First we create the nano.
Okay.
First we create.
Okay. So okay. Thank you.
Okay, sir.
So yes. Okay. So connect ma'am. Is there any student? Scholar? Connect ma'am.
Hello.
Yes. Connect ma'am.
Hello.
Hello.
Hello. Yes, sir. Yes, sir. So here we end our session.
Okay.
All the presentations are done. So
Okay,
thank you
okay,
for
okay.
sharing the session. Yes.
Okay. Thank you, ma'am. Thank you.